Recording. Oh, I'm a bit late. Okay. So we've been discussing this idea of critical points. So the setting was something like this. So we fixed a subset U in R2. This was an open set. I defined what open means last time, so it's a good idea to kind of get your understanding on this, maybe make sure that you have the right understanding of what open means. Because soon there's going to be a closed also, and similar things. Anyhow, so this is an open set, and we have a function f from U to R. And another thing is we pick a point x0, y0 in U. So then we say this point is a critical point. So this was the definition. X0, y0 is a critical point. F if either both partial derivatives exist and vanish at that point. Both partials f of x, f of y exist and vanish at x0, y0. So this is a condition that it's derived like a system of equations. Fx, x0, y0 equal to 0, y, x0, y0 equal to 0. So first of all, of course, we are talking about fx and fy. It means that we have to assume that they exist, right? So that's what we're saying. Either this or at least one of these guys doesn't exist. Fx or fy does not exist. Or either is not a very good sentence, sorry, but yeah, you understand what I mean. Or either of fx or fy does not exist. At x0, y0. So you allow yourself the possibility that this partial, one of the partials does not exist at that point. Then we call that a critical point. Or if both derivatives exist, for this to be a critical point, then they have to vanish, both. So this is so this needs a little bit of contemplation, and you have to ponder on what the meaning exactly. But now you understand why we are making this this definition. In order to make this a statement kind of in a straightforward way. So there is a theorem which your book calls Inferno's theorem. I think this is fair. It's called Inferno's theorem. Although I'm sure if you show this to Fermat, he would say, did I do this? Fermat's theorem says that or maybe before that, I have to define the idea of local maximum and local minimum also. So before that, definition, a point x0, y0 belonging to U is a local maximum. Local maximum of f if f of x0, y0 is bigger than or equal to f of x and y for all x and y such that the distance between xy and x0, y0 is less than epsilon for some epsilon positive. So what does this mean, really? It just means the following. You have this thing, you have your open set, some U. It could be any open set in the plane. It could be whole plane. It could be an open disk. It could be anything, right? It's basically good. Then pick a point here, x0, y0. So the local maximum is a point where the following thing happens. There exists some open disk of radius epsilon around this point, such that your function, the value of the function at this point is bigger than or equal to value at neighboring points. So this is exactly the idea of local maximum from one variable calculus, we just lifted to 2 dimensions. That's exactly the same idea. And of course, you can define local minimum in completely parallel to this. Right? So the idea of local minimum is that, right here. Local minimum. It just means that f of x0, y0 is less than or equal to f of x and y for some epsilon positive. Okay. So that's the thing, that's the idea. Let me give you an example of these things. They look maybe kind of daunting definitions, but they're not. They're really easy concepts. If you work with some examples, you'll see that they're trying to say something very, very natural about the behavior of function near the point, right? That's what's happening. Let first of all U be an open disk of radius 1. So U is the set of all x and y such that x2 plus y2 is less than 1. So this is U, right? So notice that I'm using dashed line for the boundary because boundary is not included because the distance from this point has to be less than 1. The boundary exactly are the points where the distance is equal to 1. So we have to exclude those points, and I use dashed lines for the boundary. So it's an open disk, and we want some open set for that. So let f be equal to square root of, for example, 1 minus x2 minus y2. So f of x and y equal to. Then what is this function? This function is really an equation for the hemisphere. That's this function, f of xy equal to root 1 minus x2 minus y2. Of course, I mean xy belonging to u, right? It's just the equation for the hemisphere of radius 1, which is sitting on top of this. So if I want to go to 3 dimensions, it's going to look like this. It's going to look like, so the graph of that function. Okay. Right. So this is your disk still, xy plane. And this is your z plane, z plane. And that's where we have drawn f of x and y. So this is the graph, right? And of course, if you look at this function, you see exactly on the boundary, which we have excluded, by the way, but we cannot. I mean, we cannot pretend that they don't know what's going on. So this is, we know what's going on the boundary. It's 0, but inside is a strictly positive. It's a strictly positive. At the origin, Higgs value 1 because yes, because x and y are 0 at the origin, and this reaches its maximum. Right? So this point 0 is a local maximum. This is origin. So this is local maximum for F. There is a question of terminology here we have to pay attention to. Namely, we are talking about the point where this the value of the function is locally maximum or locally minimum. We are not talking about the value itself. We are talking about the point where this value is attained. So two different things, right? So the value of local maximum, value at 0, 0, which is equal to f of 0, 0, is equal to 1. So this value 1 is really the value of the local maximum. But the local maximum itself happens to be at 0.00. So there are two different things. The value of a function and the point where that value is obtained, right? You have to separate these two things. Because I notice sometimes students they make mistakes about the difference between these two concepts. You ask about this, they give you that, or you ask about that, they give you this point. Okay, but an easy concept anyhow, so that's it. So now I can formulate the notion of Fermat's theorem that I wanted to discuss. Any questions? It's clear, right? So let's go to now the kind of the reason why this notion of critical point was introduced, as I said, is this Fermat's theorem. If x0, y0 is a local maximum or a local or minimum point for f, then x0, y0 is a critical point of f. 0, y0 is a critical point. So the point of this thing is that we are always very interested in finding maximum and minimum value of the function, and points where that maximum minimum value is attained or obtained. And this theorem tells us that, well, we have to look at nowhere but at critical points. They always happen at critical points. And we have a recipe to find the critical points. The recipe is either the derivative does not exist, or both of them exist and both are 0. So that's the very simple recipe in a way. So here's an example. Find all local max and min points of actually the example that I gave, f of xy equal to the square root of 1 minus x2 minus y2 xy belonging to U. And mind you that the U is the open unit disk. So this is open. Okay, so, well, I mean, so this function, first of all, is always differentiable. So there's no, so we cannot find anything about critical points by looking at points where the function is not differentiable, because the function is differentiable. So solution proceed like this, since f is differentiable, mu function. So critical points exactly are the set of solutions of this equation, right? So we have to solve this equation. F sub x equal to 0, f sub y equal to 0. But taking the derivative of this guy with respect to x is very easy. This is just minus 1/2 times 2x times 1 minus x2 minus y2 to power minus 1/2. Right? And this second one is similar, minus 1/2 2y 1 minus x2 minus y2 to the power negative. Right? That's the derivative is very simple, right? Okay, now to solve these equations, we have to put both of them equal to 0. And what can you then derive from this system of two equations, two unknowns? What can we say? Yeah. What are the solutions? Yes? X is equal to y, and what more can we say?
When x, y is 0, 0.
Both of them are actually 0. Exactly. So yes, indeed, yes. So this has only one solution, and the reason is that this is never going to be 0 because we are inside. We excluded the boundary. So don't be confused by this factor. You might imagine that, okay, so this is 0 on the boundary because x2 plus y2 is equal to 1 on the boundary. So this boundary becomes an issue, it's a very important issue. You have to gradually understand boundaries. But we have excluded the boundaries from our considerations completely, right? So we are inside this kind of hemisphere of the base. So this and that doesn't give us any contribution, so this has to be 0, that has to be 0. That's it. So if and only if x equal to y equal to 0. So there is only one critical point, namely the origin. So critical point. So just one critical point, which is 0, 0. Okay, so this point, it's a critical point, but is it local maximum or local minimum or neither of those? Still, we don't know, because Fermat's theorem is only a one-way street. It's not a two-way street. Fermat says that if is a local maximum or minimum, then it's a critical point. But here, nobody said that the converse is also true. If you have a critical point, then this is going to be a local maximum, local minimum. That's absolutely not true. You see that even from calculus 1000 course, right? You can have a function which is kind of flat at a point, but it picks up values, goes up and goes down near that point. So still, this is pretty good. I mean, we did a critical point analysis of the problem, but still we have to tell whether this point is local maximum or local. But of course, this shape tells you that. You know, I mean, there's no mistake. This is a local maximum. So local maximum. You could have told me that, well, hey, I didn't need to find critical points. I can see that this is local maximum, and I would take that. Absolutely correct. But we are doing this. We added this critical point analysis into the game just to do some little more practice. Otherwise, any questions? Yes.
Yeah. So if it was something more complicated, where we couldn't just see that it's a half hemisphere, right? Or a hemisphere, I mean. Would we have to use the definition of a local max and a local min to be able to prove it?
Yes. Then we have tools. Yes. So imagine you don't have any access to the shape of this. It's hard to imagine. But then, okay, then we go after local critical points. And then there are tests. I will tell you one test, which is important, called second derivative test, that will help us to decide if this point is a local maximum. So indeed, that brings me to the next topic, which is the second derivative test. So that's a good way to. Indeed, this is a very easy problem, but it's kind of just for visualization. So let me now give you this very important second derivative test. So we have a function f, again from u to r, x0, y0 is a critical point and is such that actually the function has second partial derivatives at that point as well. Belongs to u. Assume f has second partial derivatives on u. Assume that, also assume so the partial derivatives at this point are 0. So f sub x, x0, y0 is equal to 0, and f sub y, 0, y0 is equal to 0. In other words, it's a critical point. Just critical. Is a critical point. Okay, now, so the goal, as I said, as we discussed, is to find out if this point is a local maximum, local minimum, or what. So then there is a kind of test that can help us. So let's form this quantity. Let D equal to determinant of this matrix. So the matrix is fxx, fxy, fyx, fyy. So this is called the second derivative matrix. Of course, we compute it at this point x0, y0. So this matrix has its own name. It's a very important quantity. It's called Hessian or Hessian of the matrix. So this is called the Hessian. It's named after a German mathematician, I believe, Hesse. So it's called Hessian. Hessian matrix of f at x0, y0. I mean, what is it? I mean, because the first partials are 0, so naturally we are going after the second partials. We look at these things, and you pack them inside this symmetric matrix. It's a symmetric matrix, and you compute this determinant D, which is the determinant of the symmetric Hessian. So now, what is the test telling us? then the test says if D is positive, so there are several cases. Then, case 1, if D is positive and fxx positive at x0, y0, of course. So let me, well, everything is at x0, y0, of course. And fxx is positive, then x0, y0. When you had a function of one variable and you looked at a second derivative at a critical point, when the second derivative was positive, what could you infer about the function? It was, yes, and that point was local. No. What? It's a local minimum. That point is a local minimum. Yeah. You see, it's a critical point, so it means that the function tends to be either maximum, minimum, or one of the crazy things, none of those. But because second derivative is positive, the function indeed is like concave like that, as you said. But in fact, at that particular point is actually local minimum. Same happens here. Then is a local minimum. Second case. If D is positive and fxx less than 0, then x0, y0 is a local minimum. Oh, what did I say? Local maximum, come on. Local maximum. This is minimum. The third case is if D is less than 0. So if D is less than 0, then that point is a saddle point. Then x0, y0 is a saddle point. So we get very valuable information about the function, behavior, and shape of the function near x0, y0 without any graphing or anything, just by doing this sort of algebra, the calculation, just that. But did we exhaust all cases? No. You can have, for example, the case D is equal to 0. And you can have the case D is positive, fxx, for example, is equal to 0. So there could be cases where these things are 0. And then the test, so there's a fourth case says that in all other cases, the test is not conclusive. In all other cases, the test is inconclusive or not conclusive. Inconclusive. Now you have to understand what inconclusive means in this case. What inconclusive means that you can have this situation where it's none of those cases. The function could be maximum, could be minimum, could be none of those. Could be saddle, could be none of those cases. So you can't say anything, and in fact, anything can happen at that point, and still you're in case 4. So that's the meaning of this inconclusive in this case. So this, at least the first 3 cases, gives us conclusive results. Yeah, I mean, this is conclusive. Some cases, well, you go to your doctor and they do tests, and your test is not conclusive. They can't say anything from the test, from your test results, my test results. Yeah.
What's the case if we use fyy instead of fxx?
Oh,
Or why do we choose the second derivative of x?
yes, it's because it's here on top and down. I believe you can also change the role of x and y because nothing would change about the behavior because this is the name of the coordinates. If you change x to y, y to x, the behavior of the function, the shape doesn't change at all. And so if the determinant is that and fyy is positive, you can go. So my answer to your question, which is a very good question, is that in fact you can replace fxx by fyy, and then.
Is there ever a case where it could be such that fxx is greater than 0, but fyy equals 0?
Yes, absolutely.
And in that case, would we have to check both every time to make sure that it's a local max or min?
If that is bigger than 0, fxx is equal to 0, you have your outer block. The test is not conclusive. So you cannot go to the other one and then that also will be the same. So you don't get that.
So there won't be a point where fxx
No, that's
is,
right.
Okay.
That's right. There won't be a point that you, by being very very kind of doing an exhaustive test, you will find something new. No, you won't find it.
Okay.
Yeah, so it was a good point. Yes?
Couldn't there be scenarios where it would be easier to find fyy as opposed to fxx? Like,
No. Not honestly, no.
It's just,
Yeah, this is just, yeah, I mean, that's because that will follow the same pattern. I will give you examples and we'll look at those cases. Right. Okay, so now let's look at these examples so that we can maybe some examples so we can see what's going on. So this is the very important second derivative test, which replaces the simple second derivative test in one variable calculus, right? I mean, the situation, so I want to say still compare with calc 1000, something like that. So what was that? I mean, so we had fx equal to 0, fxx positive, x0 is a local mean. Remember? We had that. Fx equal to 0, fxx negative, x0 is local max. The other case, fx equal to 0, also, well, the only case that remains is that fxx is equal to 0. But in this case, indeed, the test is not conclusive. It's inconclusive. Test is inconclusive. Can you give me an example of this situation where both things can happen? This is calculus 1000. Yes.
like a flat thing out.
Give me an equation. Yes. Exactly. So let's look at this case, for example. So this is the case. E.g., f of x equal to x cubed. What can we say in this case? Well, this is in this case, right? Fx at 0 equal to fxx at 0 is equal to 0. And this point actually looks like this, right? So the point actually is neither maximum nor a minimum. There's none of those points here. Okay, but now give me an example where this happens and your point is a local maximum. It's not just this case. I mean, there are other cases that can happen. Yes?
You have like negative x to the 4.
Negative x to the 4. Well, why did you choose negative? You could have still.
Because then it would be a
positive.
small.
Yeah, because I said maximum, and then that's why you chose. Okay, you have 2 cases, right? So e.g., so it's another e.g., exactly as you said, absolutely. F of x equal to, let's go with negative x4. Well, in that case, your function is really like picking up at that point. In this case, fx equal to fxx is equal to 0 at 0. But the function is local maximum. In fact, it's global maximum, but that's another point. We don't care at this stage about that issue. So, and of course, you can just flip and then take x4. Take this case. This case, you have both of this, and the point is local minimum. So that really means the test is not conclusive at all. It means that any of those scenarios can happen at that point. And exactly similar thing, constructing examples a bit more involved, but this exactly happens in this case. While if something happens in one dimension, most probably it's going to happen in more interesting ways in higher dimensions. Okay, so let's now look at some examples. So see what happens. Any questions or comments? Okay. So, can you raise? Find all critical points and local max, mean, and saddle points. So let me give you this function f of x and y. So here, I'm going to give you a very simple example, x2 minus y2. To start with, just very simple example to start. Okay, so the equations here fx equal to 2x equal to 0, this tells me that x is equal to 0, fy equal to 2y equal to 0 equal to y equal to 0. So this function has only one critical point, that's 0, 0. Okay, because we just found one solution, just one critical point. 0, 0. Now the question is it a local maximum, local minimum, or is it a saddle, or maybe none of those? What is it? I mean, okay, so we have to look at second derivative then. So let's form the Hessian matrix. I don't know if in your book Hessian is mentioned, but it's a good idea to know it. So let's compute Hessian matrix. So this is the matrix fxx, fxy, fyx, which is the same as fxy, fyy. What is that? That's equal to fxx. What is fxx? It's 2x. fxy, no. Sorry, it's 2. It's 2. So fxy is what? 0. This one is 0. This one is -2. right? And then what is D? D is determinant of this matrix. So it's determinant of this guy. Oh, I'm using different notation for matrices, I'm sorry. So let's get it in curly brackets, 2, 0, 0, -2, that's equal to -4. It's less than 0. It's less than 0. So the second derivative test is telling us that this is a saddle point. So it's a saddle point. So second derivative test. Zero, 0 is a saddle. Now, of course, this is a very simple example. That's no news for us. We know that this was the kind of archetype of saddle points. I mean, this is x2 minus y2. You know, one of those graphs, z equal to x2 minus y2. What did we call these surfaces? This is a quadratic surface. What was its name? What did we call it?
Was it a hyperbolic paraboloid?
It's a hyperbolic paraboloid. It's a hyperbolic paraboloid. And this is like a horse saddle or a kind of
Pringle?
what's that?
Pringle?
What?
Like a Pringle?
Yeah, it's a Pringle, right? A couple of years ago, one of my students brought me a Pringle to class. It was very nice. Well, because I didn't know the name, you know. They brought it in, this is Pringle. Okay, nice. Thank you. Right. No, it was nicer than that. So, but so let me now give an example that's a bit more interesting. So let's look at this function f of x and y. Equal to 1 minus x2 minus y2 to the power 2. So that's a fourth degree equation. And we are asked to find critical points. And identify them as local max, local mean, saddle, etc. Okay, so now this function so let's just calculate first. Let's compute fx. What is fx? Fx derivative with respect to x is 2 times negative 2x times 1 minus x2 minus y2. That's it, right? 2 derivative 1 minus x2 minus y2. Is that correct? Really? Okay, so I trust you. Good. So Fy is equal to 2, because I was in doubt actually myself, minus 2y times 1 minus x2 minus y2. Okay, so now we have to solve this equation. This is equal to 0, this is also equal to 0. So what are the solutions?
When x, y is 0, 0, or when x squared plus y squared equals 1?
Right. So, so two things indeed. Two things can happen. either this guy is equal to 1, which in this case, then this is a critical point. Or this is different from 1, namely this factor is not 0, then both of these guys have to be 0. Right? Or x2 plus y2 is different from 1, and then in this case, xy is equal to 0, 0 actually. You see, that's the point. Okay, so let's draw a graph of these critical points, because now this is an interesting example. We have got infinite number of critical points. We have got infinite number of critical points. Why? Because the critical points are here. So if the whole circle is a critical point, set of critical points. Circle of radius 1. Or the origin is also a critical point. Here also. So we have this whole set of points on the circle, and this one as critical points. Okay, so we have solved the first part completely now. This is done. Now we have to decide whether this is local maximum, local minimum, and stuff like that. So we have to go after the second derivative. So the second derivative, f sub xx, what is that? That's equal to, if you take the derivative of this guy with respect to x, there's a factor of -4, which again don't care, but with respect to x is 1, so this is 1 minus x2 minus y2, and with this one, and then the derivative of this guy is negative 2x times x negative 2 x2 times, that's it, negative 2x2, right? I mean, the derivative of this guy is negative 2x multiplied by x negative 2x2. Okay. And for the second one, what do we get? This is also, sorry. For the second one, f yy is equal to, well, there's still negative 4 times. With respect to y is 1, which is 1 minus x2 minus y2. And then the derivative of this guy is negative 2y times y is negative 2y2, right? And what about fxy? For fxy, I mean, for example, the derivative of this guy with respect to y, we have to just take the derivative of this with respect to y now. So this is equal to -4 times x stays minus 2y, so it gives me minus 2x. So are you fine with this three calculation? This is very important because this gives us the Hessian matrix. We have to make sure that we haven't made any mistakes, because if we make mistakes here, then we cannot do anything after this step. Okay, so let's simplify those. We get something very interesting, which is the following. So this is equal to, this whole thing is -4 times 1 minus 3x2 minus 3x2 negative y2, negative y2. And for this one, we have got -4. Can I still write it? No. So let me write it here. Simplify. I don't think I did that. So let me just write it here. Get 4 minus 4 times 1 negative 3x2 negative y2. Here you get this, you simplify the negative 4 times 1 minus x2 minus 3y2 And here, of course, I have just negative times negative positive 8xy. Okay? So to start it, let's study the origin to start with, because we have lots of points to worry about. This is point and that point on the boundary. There is a question in the chat. Don't fxy have any geometric meaning? Do xy has any geometric? Yes, that's the second partial derivative, but in this case, there will be some meaning. Oh, I erased this, my God. 1 minus, this is 8xy. Okay, at 0, 0. So Hessian matrix. So we have to put everything equal to 0. So x and y is 0, you get negative 4. Negative 4. And you have here also negative 4, right? And we have got 0, and we have 0 here, because xy is 0. So D, which is determinant of Hessian, is equal to 16, is positive, and fxx is negative, right? So what do we conclude about 0? What do we say? Yes.
It's a local max.
Is a local maximum. Exactly. So is a local maximum. That's cool. Is a local maximum. Now, what about the other point? Now we have to go over the circle. What happens on the circle now? So what can you say about these things when you are on the circle? What can you say about these quantities if you are on the circle? Well, there are so many points. The question is which one you choose. But no, on the circle, there is something interesting happens, which is the following. So on the circle, well, you see, you can write this as 1 minus x2 minus y2, right? Then negative x2. So we know that on the circle 1 is equal to, so this is 0, so it's a negative x2. Negative times this, you're going to get 8x2. Yes?
Is it supposed to be minus 2x2?
Is it minus 2? Why?
No. Like it should be up above when you wrote it down.
Yes.
Should it be 1 minus x2 minus y2 minus 2?
Oh yeah, absolutely. Thank you so much. Yes. Very excellent. So this is a 0, this is a negative 2 times that, so it's 8. So the matrix is going to be like this. 8x2. What about the second derivative matrix? I mean, second derivative matrix, really, I cannot say anything. I mean, I just have to keep it as xy. This is just 8xy here. 8xy, 8xy. We don't know what that value is, but here also we can simplify a bit. So this is again going to be 1 minus x2 minus y2 minus 2y2, so 8y2. So what did we discover? What is this? D now equal to the determinant of this guy, right? We have to compute this determinant. What is the determinant of this guy? Yes.
0?
It's 0, right? Because 8, we can forget now, x2, y2 minus x2, y2. So the determinant comes out to be 0. So what happens now on this thing is that at all these points on the boundary, on the circle, not on the boundary, on the circle, the determinant is 0, d is equal to 0. So our test is not conclusive, because that's the case, d equal to 0. That was one of the cases where the test is not conclusive. But the test is not conclusive doesn't mean that we cannot say anything about the function at that point. What can you say about the function still at that point? So you have to graph. You have to graph. Either you go to your graphing softwares and use brain power a little bit, and some methods. You have to graph. If you graph, you get something. You discover something very, very interesting about this curve. So let me draw the curve for you, the surface for you, and then you see why. Okay. Any questions? We're going to be finished in 2 minutes. So graph of this function. You see, this is not one of those cases that we studied, right? Because this is not a quadric surface. This is not a quadric, this is 4-degree surface. This is degree 4. Nevertheless, you can graph it exactly. It's going to look like this. It's a sombrero. Mexican hat. This is the graph. You see, this is the circle. This is the point 1, which corresponds to the origin. And these points here is a circle, exactly the whole circle, x2 plus y2 equals to 1. This graph is a very, very famous, well-known graph in physics. I'm sure you have heard about, for example, Higgs particle. This is Higgs potential. This is what made Higgs and all that kind of physics also interesting because of this graph. So let me now 1D case of this f of x equal to 1 minus x2 squared. So you can gain something a little more about the nature of this function, nature of this function by looking at the 1D case of it and then go to 2D. So how does it look like? It looks like this. This is very simple in this case. This is f of x. Here is 1, here is minus 1, this is 1. This graph you can do it. That's high school stuff, right? We can do that. Okay, so how this graph is obtained from this 1D case? How you go from 1D to 2D? Well, we simply replace x, x2 by x2 plus y2, right? We just replace it by x2 plus y2. It just means that this graph is obtained by rotating this around this z-axis, and then you get that sort of sombrero, Mexican hat. So now we can see what's going on at the bottom of the kind of valley here. Indeed, this point is a local minimum, but is not a kind of non-degenerate critical point that can be we can understand the nature of this point. Let's look at this point, the second derivative of this at that point, by the way. So f prime, let's look at f prime of x. What is this? This is equal to 2. I mean, okay, 2 times minus 2x times 1 minus x2, right? And let's look at f double prime of x. What is that? That's equal to negative 4 times x, and then negative 2. Okay. Oh, what am I doing? This is 1 minus x2, and then there is negative is negative 2x times negative 2x2. So this is equal to 1 negative 3x2, so it's negative. No, I made a mistake here. I'm pretty sure I made a mistake. So I'll let you compute the second derivative at this point. It's end of the day, end of the week, so it's we have already gone 10 minutes over time. So this is easy, but this point is not. So the test at this whole circle is inconclusive. Okay, so guys, have a good weekend, and we should just finish now. Thank you. Any questions? Yes.
If by Fermat's theorem, any like local min or max has to be a critical point, why didn't we find the bottom circle as a critical point when we were finding the critical point?
Oh, those are critical points. Indeed, these are local minimum.
So but why didn't we find them when we tested it?
Yeah, because the test is not a very powerful test. Yeah, because the thing is, the test is really useful. It's kind of good only for non-degenerate critical points. But then when like you have something like that, or something comes like, consider like x4. This touches this point. The touch is actually, you see, it's like a third order touch, because the third derivative at this point is also 0. So it's a third order touch. That's why you can say this point is a local minimum, but our test is not conclusive. The test cannot tell us a priori, just purely algebraically, that this point is a local minimum. Although we know that it is. We know that it is. Similar thing happens. So these tests are general. I mean, so can we go to, let me just stop this thing. Pause the call.